Okay, welcome to Chapter 3, Section 1. This is your second video lecture of the year, and let's get started. Let's talk about the three states of matter. This whole chapter is actually going to be about these three states of matter and how they change and some interesting properties related to them. So we're going to first kind of start out with a thought process. Okay, so in the kitchen you might find three different forms of water. What are these three forms of water, and where exactly in the kitchen would you find them? Take a second, think about it, write down your answer below. So, if you've thought about this long enough, should have thought of the three forms of water, right? Which we know are liquid water, we know are solid water, otherwise known as ice, we know as gas. So, the gas form of water, which we know as steam. So if you can think of all three of these different forms, you can easily come up with the example. Your textbook uses someone holding a cup of hot chocolate or a cup of coffee, right? So we know the hot chocolate is liquid, right? You can see the liquid right there. It's got this kind of moving, flowing kind of body to it, and it's steaming, right, because it's so incredibly hot. And then we can also cool it down. Let's say it's too hot, right? I can take a chunk of ice, put it right in that hot chocolate, and cool it down. So right there, we've got all three of the states, right? So the solid, and if we're talking about water, is known as ice. We know this as just straight plain old water, and that we know as steam. If we're talking about the three states of water, so this is just for H2O. So these things are all different when you're talking about other substances, right? But every substance, if you think about that periodic table that's in my room, you've seen it a million times. Any material on the planet can be in these three states of matter: solid, liquid, and gas at one point. Water is just the one we kind of think about the most. So done today, I want to do three things. I want to describe the properties, describe the all particle share, describe the three states of matter, and explain the differences between them. So you should be able to be given like a question, and should be able to identify that state of matter just based on some properties and characteristics we're going to talk about today. Okay, so next, let's talk about the particles of matter. So these are the physical forms in which substances can exist. This is how we interact with them on Earth, right? So any substance can be in one of these three forms. Okay, so it's interesting to note that this is for all matter. So even the desk, the chair you're sitting on right now, the desk you're working at, can be made into a gas or a liquid. So if you're wondering how would you do that, well, you would apply heat, right? So all matter can be in the three states. So there's other forms of matter too. Also, I wanted to point out too that states of matter, sometimes you'll see them called the phases of matter. States of matter is the proper name, but phases you might see in like another textbook. If we do another activity online this year, you might hear them called the phases of matter. So other forms of states of matter are plasma, superfluids, colloids, and there's actually many others. I'm hoping to get you guys to do a little research on some of these kind of crazy states of matter that are out there too. We are going to get to plasma at the end of this presentation as well. So matter is made up of tiny particles. You guys know that. Atoms and molecules. These particles are always in motion. So they're always moving. So as you go about your room right now, things seem stationary. Things seem like they're not moving. But down on that molecular level, down on that tiny, mini level, they're actually moving. They're moving a little bit. And the different states of matter move at different speeds. I'm going to get to that in a little bit. So that's something we actually want to pay attention to, is how fast they're moving. And if we go back up to my example before, remember I said all forms of matter can be made into a solid, liquid, or gas? Well, the amount of heat has something to do with that. More on that in a second. So the particles of matter interact with each other in three ways. So if you want to tell the difference between the three states of matter, pay attention to three things. One, how fast the particles are moving. Two, their position relative to one another. And three, their temperature. So these last two right here are especially related. They're kind of connected, right? So think about to yourself, what makes sense? Something that's hot, it's moving faster, something that's cold. Like what would kind of make something move faster? More heat, right? Think about when you boil water, right? The water is kind of still at room temperature, and as you add heat to it, it's moving, right? It's actually moving faster. So that's the kind of logic example I'd like you to think about. So the faster these molecules actually move, the more heat they have, and the different state they'll be in. So the way these particles interact with each other also helps you determine the state of matter. So are they bouncing off one another? Are they lying right next to one another? Do they have almost like a bond together? Are they flowing past each other? So this interaction is key to note as well. Okay. So let's look at what these interactions kind of look like on the next slide. So here we have the three states of matter. We've got solid, liquid, and gas. If you look at the first picture all the way on the left, there's a strong attraction between them, right? They're kind of orderly. See how close together they are? There's not much space. So they've got a unique quality in that in a solid, the particles want to be near each other. They want to line right up, and they want to stay stationary, and they want to just hold a certain structure, right? So they have a more solid structure, we could say. Oop, my pen is not working well today. They have a solid structure. Over here, with the liquid, they're moving faster. So as we go from left to right here, you can kind of think about this as the speed of these molecules increasing. So we're going to write faster as we go from left to right. The liquids, as I said, are moving faster. There's some attraction between them, but less attraction than the solids. They slide past one another. They are kind of attracted to one another, but they're not quite there. They don't bond together. They don't kind of hold that same position, which explains why they don't hold a shape. But liquids tend to fight holding any kind of common shape. If you grab your water bottle and you slosh that water around, you can see that, right? That they will move really easily. They'll flow easily. Gases, even more so. So they're moving even faster, right? You've got the speeds approaching a really fast speed, and they're actually bouncing off of one another. They move independently of one another, as it says here. So they don't need to be next to each other in a pattern or a shape. They'll go anywhere. They'll kind of expand to any position that they can. So let's start with solids. Let's focus in on solids a little bit. A solid is a state of matter that has a definite shape and volume. So a solid is going to be a solid not no matter what, but it wants to stay in that solid shape, right? So you've got a cube here. That cube is set in that shape, and it's going to remain in that shape unless enough energy is applied to it. So despite seeming like it's motionless, the particles in every solid is actually moving. So these particles actually vibrate in place. So the fact that they move is interesting because we can't perceive that, but they move just enough so they don't lose that bond. They don't overcome the attraction between them here. So your pen you're holding, those particles are moving, but just not quite enough to break their shape, okay? So think back to ice, right? So we know ice retains that ice cube shape, that whatever shape it's frozen in, until something happens to break those bonds, right? And we'll get to that in a little bit. So continuing to talk about solids, they have this force that holds them together. So solids don't flow. So that's a direct contrast to liquid, right? So we can contrast solids to liquids there. The particles in solid can't change places, so a solid will keep its shape unless you break that. Solids can be strong. Think about steel, iron, titanium. Those particles are really close together in those strong solids. So compare titanium to gold. There might be less of a bond, or they're less close together in gold because gold is a lot softer of a metal. It's not possible to pass through solids without breaking them, is another key thing to remember. All right, so contrast that with liquids, right? Think about it. Can something pass through a liquid easily? Yeah. Can something pass through a gas easily? Yeah. I mean, you're doing it right now when you're moving in our atmosphere on Earth. So solids have that kind of ability to block things, stop things. They are so condensely packed together that they'll stop an object from moving through it. So there's two kinds of solids. We kind of put solids into two groups. Crystalline solids have an orderly three-dimensional arrangement. So iron, diamond, and ice. And in quartz, which you can see down here, which is a type of crystal, Think about that should be that should be your key to remembering that, right? Crystalline solids. They're really orderly. So they follow a pattern and structure. So each of these molecules is structured like this, but also holds this pattern where you can see the same exact arrangement after every section here. Okay. Amorphous solids are different though. Those are made of particles that don't have a special arrangement. Glass, rubber, and wax are examples of amorphous solids. You can see here there's like a common structure. They kind of look similar, but the pattern isn't continuous. You can see it kind of change. Like here, you've got a molecule that's much thinner, one that's wider here. They might have the same number of atoms and protons and electrons and things like that. Their atomic structure might be the same, but the structure of the molecules next to one another is different, okay? So that means that their bonds are a lot easier to break. Think about the pliability of rubber, how you can kind of squish rubber down versus quartz or crystal or diamond. Think about how much harder those crystalline solids are. So now, here's some more examples that I kind of talked about. Your crystalline solids over here, your amorphous solids over here. Here you've got glass, rubber here. Your table salt here is quartz. So just remember that you can see this orderly pattern here versus sort of this just all over the place pattern here. There's no real regular pattern here. So liquids are the next state of matter I want to talk about. They have a definite volume, right? So they take up a certain amount of space. They will, if you pour a liquid into a container, it's going to stay in that amount of space. But it doesn't have a definite shape. It takes the shape of its container. So I'm going to write down up here, no definite shape. Okay? So a liquid will change its shape depending on what you put it in, right? So if I have a SpongeBob SquarePants mug that's shaped like SpongeBob SquarePants, if I pour my liquid in it, it's going to take the shape of that mug. It's going to take the shape of SpongeBob. So no matter what shape you're putting it into, it's going to flow to that shape. So these, remember, these particles in a liquid move a little faster, and just enough to overcome some of the attraction between them. So your molecules are going to stick together a little bit, but they will definitely move more easily, and they slide past each other. That's a key term to remember, that sliding motion. So there's two characteristics that liquids have. These are like special properties only for liquids. First are surface tension. So this is a force that acts on the particles at the surface of a liquid. So if we're talking about some kind of container of liquid, on the very surface is where you can find surface tension. It's sort of what explains why some things can kind of remain on the top. It kind of shows that this sort of bond, this adhesion between molecules of a liquid. When we talk about viscosity, which is the second characteristic, this is how a liquid is resistant to flow. So some liquids are more viscous than other liquids. Some liquids, I don't want to use the term thick, but they kind of flow. It's more difficult for some to flow than others. Let me give you some examples of that. So toothpaste. Toothpaste has a really high viscosity. It's think about how it just takes a lot of energy for it to flow versus something else. So we have honey down here is a higher viscosity than water. Over here, you have an example of surface tension. So this paper clip will float on the water because the bonds of water want to hold together at the surface of a liquid. And that's true of every liquid. Some liquids have different surface tensions. For example, I think your textbook talks about gasoline has a lower surface tension. So if I put that paper clip in a vat of gasoline, we would see it probably sink more easily because its surface tension is lower. So just remember that surface tension occurs at the surface of the liquid. Okay, my handwriting is fantastic. All right, so let's get on to gases. Gases is a state of matter that has no definite shape or volume. So this case, now we're out the window completely. Liquid, if you think back to it, had a definite volume, but gas does not have a definite volume. The particles of a gas move quickly. So another way to say that is that particles of gas expand. All right? The amount of empty space between gas particles can change, right? There's this expansion that's always happening with gas. Gas is spread out to fill a container, all right? This is because they're moving fast and there's no forces to stop them from flying apart. So imagine this is a cloud of gas, right? This is like a cloud of gas. It's always going to expand outward and keep going to whatever container it's in. So, you guys are what, in 8th grade? When you think about gas, you think about farting. Fine. That's a perfect example to help you remember how gas expands. If somebody farts anywhere in the room, that gas is going to slowly expand, and that explains why if I fart in the front of the room, I can smell it in the back of the room, right? Because that gas is going to expand and slowly fill up the container of the room, right? Unfortunately, I wish farts did not do that, but unfortunately, that's what gas does. It doesn't have a definite volume, right? So it might start out this size, but then slowly expand out to something bigger, right? To a larger volume. So gas expands. Remember that. So I said there are 3 states of matter. There's actually 4. There's a hidden kind of 4th one. I'm going to put air quotes around this 4th one. So this is the air quote 4th state of matter. So plasma exists when particles are superheated. So plasma only exists at a very high temperature. Results when atoms break down. So the thing about neutrons, protons, and electrons, right, that are inside of an atom, well, those actually get kind of freed up in a plasma. They're kind of floating around in this goo of energy, and that's plasma. So it's a fluid, like a goo, kind of. I'm gonna say it's not like a goo, but it is. It's present only because we call it a liquid because it kind of has that flow the liquid does. However, think about plasma more like pure energy, okay? Lightning is an example of plasma. So if you think about the sun, right? There's a sun beautifully drawn for you. In the center of the sun, that's plasma. That energy, that pure energy inside of the sun is plasma, okay? Fire, when it reaches certain really high temperatures, that's plasma energy there, okay? So while we're going to do a little bit more on plasma later in the unit, technically when we say the 3 states of matter, you don't always include plasma, but, it is a state of matter. It's that kind of hidden 4th one. All right, so that's it for this section. I hope you have taken all your notes. Please watch this video as many times as you need to, and have a great day, and do not fart in my class, ever. Thank you.